In this final video about vectors, or at least our introduction to vectors, we want to work with some applications. And so here's the first application. And when we say application, it's really code for a word problem, right? So this one's talking about a paper airplane and it's thrown due north, traveling at a certain rate. And then there's a breeze coming from the northwest, so it goes southeast, that slows the plane. And so we're wondering, where does it end up, right? That's kind of the overall question. So if we just model this using a picture. So we want to draw a picture of the motion that's going on here. So we have a vector, and I'm going to call this vector v, and we're going to say that this vector v, okay, we know its direction, it's due north, okay, so we'll interpret that later, but we know that the rate or the amount of travel that it's going with is 2. Okay, that's how much speed it has. Okay, and then we also know that there's a breeze, right? There's another breeze that is coming from the south or from the northwest heading southeast, so that would go something like this. And then I'm just going to place it at the tip of V. So I'm going to draw it like this, and I'm going to call this W for wind. And we know that this wind has a magnitude of 0.3. Okay, we're talking speed. Okay, so then where's the resultant? Well, the resultant, again, you could create the parallelogram. Okay, so you have something like this and then like this, and your resultant would go from the shared initial point to wherever they both end up, that diagonal of the parallelogram, or you can just go tail to tip if you want to avoid the parallelogram. Okay, but this is going to be the resultant, and I'm going to call it R for resultant. Okay, and that would be the actual path that the plane follows because of the wind that is being applied to the airplane, or the paper airplane. Okay, so we want to know how much the magnitude is, and we want to know the direction. We want to know theta. So the direction is going to be a little tricky, but we'll get there. Let's go ahead and work on the magnitude first. Okay, so if we take a look here, we already know magnitude of two sides. Okay, and normally we're like, okay, well, if we were in a right triangle, we could just use the Pythagorean theorem and we'd be done. Well, we're not. Okay, but the question is, what kind of triangle is it, or how could I do this? And so if you might remember back to the previous example where we were looking at the angle and direction, or sorry, direction and magnitude of a resultant vector, we ended up using law of sines or cosines, and that's exactly what we're going to do here. But the question is, how much is this angle? Okay, because then I'd have a side angle side scenario, which would mean I could use law of cosines. Okay, and to answer this question, so I want to know this angle, and I'm going to call it alpha. I'm going to maybe just ask us to think a little bit more about the scenario. Okay, how much is alpha? Well, if it's going southeast, how far is southeast from, well, I guess south, okay, or north. So we're looking for this angle here, and so if this is pointing directly southeast, and we treat this vector as south, this would be 45 degrees. Okay, so doing a little bit of geometry there, making a little implication, and your model, if that 45 degrees is not correct, it's an assumption that you're making in your model, and we would use it as we go forward with grading. So, but I think in this physical scenario, it is safe to assume, since it's heading southeast, that the angle between the vector v and vector w here would be 45 degrees. Okay, but I digress. So we want to figure out what r is. So I'm going to use law of cosines to say magnitude of the resultant is equal to magnitude of the velocity, or the square of each of these, sorry, the square of v plus the square of the length of w plus minus 2 times magnitude of v times magnitude of w times cosine of the included angle, which is alpha. Okay, so then this is equal to 2 squared plus 0.3 squared minus 2 times 0.3 times cosine of 45 degrees. Okay, and if we do this calculation, get, let's see, so, and if I square root this, I just get that the length of the resultant vector is 1.8, if I round to one decimal place. Okay, so now I know the length, or the magnitude of the resultant vector. It's just 1.8. Okay, so there we go. Now, how do I find the direction? How do I say something about the direction? This is going to be a little difficult, okay? Typically, I like to think of direction as, from our initial point, how much is this elevated, okay? So what I could do is find the angle in here, let's call this beta, okay? And then subtract beta from 90 degrees, okay? So I'm going to say this is going to be 90 minus beta, okay? And let me color code that so it looks all pretty. There we go. We got to have things looking nice. Okay, 90 degrees minus beta. Okay, so the question is, how do I find beta? Okay, well, this is where I have to look at my triangle. I know, let's see, two sides and the included angle. I know the side. I think I could actually just use law of sines if I wanted to. I could do sine. Let me do this in different color. Okay, so I could do sine of beta over 0.3 is equal to sine of 45 degrees over, now I know that's 1.8. Okay, and then I can manipulate this equation and solve for beta, and I would get beta is 6.7, let's do 6.8 degrees, okay, after our inverse sine and everything, okay? So then theta would be 90 minus the 6.8 degrees, and if I do that, I get that theta is approximately 83.2 degrees. Okay. Now, typically in a scenario where we're given this, we understand what theta is, or like what we mean by degrees, and we would measure it in standard position. But really, when we're describing it, we should say 83.2 degrees north of east. Okay. So what that means is here is east, right? If we consider that direction, we're 83.2 degrees north of that, okay? So that's typically how we describe directions in physical contexts, okay? But anyway, we now know information about the resultant and the resultant's direction and magnitude. That was our goal. So we're done, okay? And I should say we should write out a lovely sentence for all this, but I'll leave that to you. All right, next one, okay? Boat ropes tugging on a heavy rock. I want you to pause the video, see if you can draw a picture and label it. Resume the video when you're ready to see the setup. Here's my setup. Okay, so I drew, vector v and w. V is length of 70 in one direction. I just made it go to the right to make things simple. And then w is 35 degrees north of east from there. And so then that has a magnitude of 55. And then I just completed the parallelogram to get the resultant vector drawn in. Okay, and so now we want to find the magnitude and direction of the resultant pull. Okay, very similar to what we've already done. This one, though, we do have to remember that bit about parallelograms to help us move forward. And in that, the opposite angles of parallelograms are congruent, so that's 35. So if these are both 35, those sum to 70. Interior angles of a parallelogram sum to 360. So to find this angle here, alpha, okay, we have to take 360, subtract off this 70 that I found, which is 2 times 35 degrees, and divide that result by 2, okay? And if I do that on my calculator, I get 145 degrees. Okay, so that's my angle alpha. Okay, and then again, to find the length of the resultant, to find the magnitude, I'm in a scenario where I have a side and the included angle and a side, so that's law of cosines again. So I'm just going to jump straight to it and say magnitude of r is equal to, and it would be the square root of the first vector, length of the first vector squared, so 55 plus the other vectors, the length of the other vector squared minus 2 times magnitude of vector 1 times magnitude of vector 2 times cosine of the included angle, which is 145. Okay, and then I number crunch that in my calculator and I get the magnitude of the resultant to be 119.3 pounds if I round to one decimal place. Okay, Great, so we found that, and now we need to find the direction. And again, I would typically call this angle down here, this theta angle, that as the direction. And so if I want to find that, I know it's going to have to be smaller than, so I'm just going to say this is going to be smaller than 35 degrees. Okay, so that's kind of a reality check. But how do I go about finding that? Again, what I could do is find angle beta and say that if I want to look at theta, that's going to be 35 minus beta, okay? And beta I can actually find via the law of sines, okay? I can do sine of beta over 70, so 70 is opposite of angle beta, is equal to sine of 145 over 119.3, and then if I solve for beta, I get approximately, I'm going to say 19.7 for this, and then that means that theta is 15.3 degrees, okay? So in all, I can say that the resultant's magnitude is 119.3 pounds in the direction of 15.3 degrees. Okay, now I don't necessarily want to say northeast, any sort of compass direction here, only because I made the assumption to put V along the east direction. So avoid that if at all possible. But if you are given a context where north, south, east, west are defined, you could say in this instance it would be 15.3 degrees north of east again. Okay. Equivalently, you could also say it's, well, no, never mind, you can't say that. I was going to say you could mention it as 19.7 degrees east of north, but actually this vector W doesn't point north, does it? So that is an invalid description. But we could still say 15.3 degrees north of east if we were given that V points due east. But there we go. We have some more examples in context with vectors. So again, drawing them is super important. Remember the parallelogram law. If you're adding them, the resultant is just what you get when you add them. And to make use of the law of sines and cosines as we go through, okay? It's kind of a neat application. So there you go. And now we know a little bit more about vectors.